Very good. So
Okay.
welcome everybody. So this is the third seminar from our seminar series on for working group 1 of the relativistic quantum information cost action. So our working group, the topic of the working group is quantum QFT aspects of quantum information, and this is quite broad, and we've had quite a few different talks coming from different operational approaches at the interface of QFT, gravity, and quantum information. And the hope is to continue with one seminar every month on these interesting topics, except during the holiday season. And as you can see, we're all being recorded. This will be available on the RQI Cost, the YouTube channel afterwards. And yes, we're very, I guess Kasia will introduce our speaker as well. So I'll pass it on to Kasia.
Thank you. Yeah, so it's my great pleasure to welcome today Leon Loveridge, who, long time ago was a PhD student here in York, but right now is even farther north at the University of Southeastern Norway. And today he's going to tell us about an invitation to operational quantum reference frames. So please, Leon, go ahead.
Thank you both for the invitation and the introduction. Yeah, so I'm Leon. I'm a mathematical physicist. So my work is somewhere in between the communities of math and physics, and I think I'm viewed with suspicion by both sides. So I'll talk about some work that's been going on in quantum reference frames. By now, there is a whole host of different approaches and different frameworks to this subject. So I've put the word operational in front of it just to highlight that this is only one way of thinking about these things. And there's a bunch of others as well, which I'll sort of mention as we go along. Let me just play around with my screen a little bit so I can actually see what I'm saying. Yeah. Okay. So there are many ways to motivate this subject. One way is to say, well, quantum mechanics or maybe quantum field theory is a good theory of the world. It's precise and accurate and it describes what we see. So that's one sort of starting point that we accept as being a reasonable claim. I'll jump to 3. So 3 is maybe more controversial, is that quantum mechanics is somehow a universal theory or quantum field theory. So it describes everything, at least in principle. And the second, number 2 here, is that what's truly observable in the world is somehow invariant under something, some symmetry group, some gauge group, something that we believe is a fundamental reason to say that, well, those things which can be genuinely seen have to be invariant. So I think this is probably the one that needs the most explanation. But if one accepts these 3, say, tenets, one is led naturally to the subject of quantum reference frames. Oh, by the way, I should say I'm happy to, since there's so few people and it's sort of informal setting, I'm happy to be asked questions at any point or clarifications if I say something that doesn't make any sense. So, for example, in standard textbook quantum field theory, fundamental particles are associated with irreducible representations of the Poincare group, in a sort of Wigner's point of view. But of course, irreducible representations commute with, well, the unitaries in the irrep commute with everything that's non-trivial. So therefore, we have a problem that somehow, well, what's observable then? If we have a single fundamental particle, and everything has to, by some Schur type lemma, everything should commute with the unitary representation, then we say, well, the only things that can actually be observed of a fundamental particle are operators proportional to the identity, for example. So there's a bit of an issue. So there's 3 principles that lead us to thinking about quantum reference frames, I would say. But as the old joke goes, if you don't like these principles, I've got others. So one can think perhaps more broadly about Einstein's original sort of mindset when he was thinking about special relativity in the beginning and thinking about, well, how do we actually measure things like lengths or time intervals in the physical world? And he did a sort of operational analysis of physical clocks and rods that we say, well, if we want to say that something is a meter long, we should have something that's a meter long in the world with which we can compare it to, if you like. So the upshot here is that the statement in bold here is that whatever reference frames we're considering, they should be described by the same physics as the systems that they're describing, or the systems that we're trying to describe relative to them. So that's there's various ways into the subject, but I think once one convinces oneself that it's worth thinking about, then it's not too hard to get started. So there's a lot going on at the moment. So this is a subject that's sort of taken off in the last 5 years or so. So there are some recent, well, so this one's not really out yet. The first one is, well, what actually is quantum mechanics about? If the framework that we use doesn't involve a reference frame or a quantum reference frame, but we believe that there should be a quantum reference frame, then maybe we should try to understand what the standard formalism of quantum mechanics is actually telling us about, since there's a reference frame that's there but not really being explicitly described. So that's something I'm trying to figure out at the moment. The whole business that really started this off is frame changes. So this is the Bruckner and Flaminia and Esteban paper from 2019, where they consider consistently, say, moving between different quantum reference frames in terms of describing a trio of physical systems. How can we have a consistent description where there's no external frame and we want to describe two systems relative to a third, and then say, well, if we have that description, how do we describe two others relative to another one, and so on. And then one has to consider things like superposition of frame states, for example. This business has now been analyzed in the operational framework in this paper down here. Again, some more recent work is on uncertainty relations. So if we believe that quantum reference frames should be everywhere in quantum mechanics, in some sense, one has to go back to all of the main results and say, what can we do to reinterpret everything that we know about quantum mechanics relative to a quantum reference frame. So I'll say a little bit about this one in a minute. And the third is this recent work on what we'll call type reduction in algebraic quantum field theory. So this is really the only relativistic part, perhaps, of this talk in terms of serious relativity theory. And what we'll see is that somehow the incorporation of a QRF into quantum field theory really fundamentally changes the structure of the algebras, the local algebras that we use to describe quantum field theories. So I'll talk a little bit about, well, really 1, 3, and 4. I'm not going to say much about frame changes in this talk. Okay, I will press on. So one thing that distinguishes this approach from other approaches is the sort of fundamental rooting in the operational structure of quantum theory. So this is a little bit different from certainly the perspective neutral approach, which is maybe the most famous approach at the moment for understanding quantum reference frames, which is motivated by quantization of constraints and so on, but is not founded on these operational ideas that in the same way as the operational framework. So I'm going to zoom right out and start off by saying what we mean by operational theories, just in physics. So this is not quantum mechanical, this is just anything. So somehow the most basic experiment we can do is a prepare and measure scenario. We do something over here, we register something over here. So it doesn't have to be a human. That's one of those things that's, I think, misunderstood about the operational approach to quantum mechanics. It can be sort of automated in some way, but it's just a basic physical experiment. So we think about preparations as production of systems or manipulation of systems in some way, and measurements as just registration on some screen, if you like, some outcome. So we'll call the preparations states and the observables measurements. The registration procedures observables, I should say, for reasons that should become clearer soon. So all we want to do is look for essentially correlations between the preparations and the outcomes in a particular measurement. So we can just say we have some finite set of possible measurement outcomes, and we just record how many times each outcome occurs in a repeated run of the same experiment. and we can collate these numbers together and write down probabilities as the sort of long run frequency of the relative frequencies of the times that a particular outcome occurs. Nothing complicated at all, but there is some extra structure here. So we can mix preparations. We can do one preparation with a certain probability, another preparation with another probability, and add them together in a convex way. So there's a convex structure on the set of states. And if we call the association between a preparation and this probability an effect, we then want to say, well, the effect should extend to affine maps on the convex state space. One can turn this around, put a convex or even a linear structure on the set of effects, and then we have this sort of double dual embedding where we can say, well, the effect is a functional in the states, and we have some state functional on the set of effects. So we have this state effect duality, and so on. And there's a lot of structure here, actually. So I'm not going to go into that this much in this talk. I'm not sure exactly everybody's background, whether they're mathematicians or physicists. But actually, if one has something a little bit extra called total convexity on the state space, one gets these nice structures called base norm spaces and order unit Banach spaces, which already gets us sort of some way towards the quantum mechanical situation, but not all the way. So we could then call an observable an effect-valued measure. So it just eats an outcome and gives us one of these affine functionals. And as usual, we think of pure states as being the extremal elements of the convex space of all states and so on. So two examples of operational theories are, of course, classical probability theory and quantum theory. So classically, we think of states as probability measures on some space of outcomes. Pure states are just the points or the delta measures. And the state spaces are simplex, which means you can just decompose any mixture in terms of, uniquely in terms of pure states. So that's the fundamental characterization of the state space of classical operational theories, probabilistic theories. Think about observables in various different ways. Effect-valued measures is the basis, but on the extremal effects of the pure effects give rise to observables, which correspond exactly to real-valued functions on the outcome space. And this recovers sort of algebraic classical mechanics, if you like. So this space of continuous functions is going to be a C-star algebra with a natural involution and so on. I think there's a question.
Hi, Leon, just a quick clarificatory question I wanted to. So is this similar to the generalized probabilistic theories or operational probabilistic theories approach, or more general, or how does it connect?
Yeah, I would say it's exactly the same. I mean, it's maybe not the exact way that people normally do it, but yes, it's exactly the same. So this is just putting classical probability theory as a general probabilistic theory. Yeah.
Okay, thanks.
Yeah. So yeah, if we just go back to the previous slide. Yeah. So this where should I say it? Basically here. So states is a convex subset of a real vector space, and observables or effects as affine functionals. It's exactly the structure. Yeah, thanks.
Okay, thank you.
But what people don't normally do is then say, well, what's an observable as a sort of effect valued measure? So that's something I think is missing actually from the GPT literature a little bit, and also the connection maybe to sorry, is there? Yeah.
Probably the connection to the algebraic point of view. This is what you're about to say. That I haven't seen.
Yes, exactly. So exactly how to recover the C-star algebra of observables as, yeah, say continuous if omega is finite, or continuous and compactly supported if omega is just locally compact, for example.
You need some additional constraints to get the C-star algebra, the structure of a C-star algebra?
I mean, so if omega is compact, then you just need to consider, well, the real valued functions. Well, sorry, all functions would give you, I shouldn't say real valued here, I should say all functions here, would be a C-star algebra under the natural algebra product of functions, and involution is just complex conjugation.
Okay.
Yeah.
Thanks.
Yeah. then one has various sort of nice structures in terms of Gelfand spectrum, recover the state space and so on. So algebraic classical mechanics can be recovered from this general operational structure in the case that we just consider extremal effects. Another very good example of an operational or general probabilistic theory is, of course, quantum theory. So here we start with a state space, which is going to be a convex subset of the space of trace class operators. Maybe the self-adjoint, maybe the positive trace class operators, which can be realized algebraically just as the pre-dual of the space of bounded operators in some Hilbert space. If one can then show that the affine functionals on this state space are exactly bounded operators sort of living in this unit operator interval. So those are the effects. We can think of omega as just some quite general topological space. So those are the outcomes of a measurement, a potential measurement of some observable. And the observables are positive operator valued measures. So these are the things that spit out an effect on the right-hand side of the map, and they're positive and they add in the right way and so on. So I'm sure this is quite familiar to everybody. But it's nice to see that you can realize quantum theory as just a special case of this general operational structure. Of course, sharp observables, so those are the ones that most people deal with, particularly in quantum field theoretic settings, are the projection valued measures. So these are the POVMs which have values in the projections on the Hilbert space. And of course, we then have all of the machinery of the spectral theorem and so on, and we recover self-adjoint operators and the algebra of observables as C-star algebras and so on, or perhaps von Neumann algebras. So the point here really is to say that if one starts with an experiment and thinking about just literally writing down probability distributions for prepare and measure scenarios, there's not really a good motivation to say that we should be considering self-adjoint operators, even if we know that the systems that we're discussing are quantum systems. It's much more natural, I would say, to say observables are POVMs, and there's a particular class of POVMs that give rise to all of this extra stuff. Which is not to say that it's not a very successful description, but there's just more to it. So, of course, the Born rule goes through as one would expect by just taking traces. But one of my favorite unsung theorems in Hilbert space theory is that POVMs, so even if we get out of this just general operational background, but just look at the sort of so measure theoretic structure of Hilbert spaces, and we take any function on, say, a sigma algebra of subsets of a topological space with values in the bounded. Sorry, this plus is in the wrong place. These should be positive operators on H. Then this map is a POVM if and only if for every unit vector, or for every vector in the Hilbert space, you get a standard scalar measure. So this is saying that POVMs are exactly the right thing in the Hilbert space framework to generate probability measures. Okay. So I've been told that I put way too many mathematical details on my slides. I'm incorrigible and too old to change, so I'm going to instead try to give a sort of take-home message at the end of each bit of technical stuff to say, well, what was the point of talking about that? So POVMs, well, they fit with the natural probabilistic structure of Hilbert spaces. They arise naturally in measurement. I'll talk about that in a minute. They have two, I think, in my mind, fundamentally different interpretations. So one is that you can literally just sort of add some classical error, some classical noise to the sharp version. So by sharp, I mean self-adjoint or PVM version of quantum mechanics. So you can sort of, degrade your good theory in some way. But you can also, there are also observables that are sort of fundamentally unsharp, fundamentally not projection valued, which I'll call intrinsic unsharpness. And I'm going to talk about those next. But I think there's lots of other good reasons to consider observables as being more general than self-adjoint operators. And one of my favorite other reasons is that we can phrase the standard undergraduate idea of incompatibility in a much more operational way. And what I mean is that we can say that if you have two POVMs, so A and B, on separate outcome spaces, we can say that they're compatible exactly when they give rise to joint probability distributions for all states. So we say that they're so if I phrased it the other way around, so POVMs A and B. So if there's an M that we'll call a joint observable for A and B on the product, so that you get all of the marginals out again, then we would say A and B are compatible. So we marginalize over the outcomes of B, and we just get the POVM A back again, and so forth for B. So what this actually says is that there's a joint observable, so the probability distributions you can generate for A and B separately can be merged into a joint distribution for M. This does not entail that A and B commute effect-wise, element-wise. So it's much more general than the standard framework of, which is not, I would say, operationally motivated, that we say that two observables, self-adjoint operators, are compatible exactly when they commute, and then we appeal to sort of something like simultaneous diagonalizability or something, and it's not completely clear. I'll talk about this more again in a minute. If one of them is self-adjoint, one of them is sharp, then compatibility is exactly equivalent to commutativity. So it's a genuine generalization. So the POVMs of interest are going to be covariant ones. So this is where we're going to have a group representation. So most of the ones that I introduce now are going to be covariant POVMs, and I'll say exactly what I mean by that. So my infinitely many POVMs coming up. So the ones that I'm most interested in personally are the ones that are these sort of intrinsically unsharp ones. So there's this old theorem by Pauli that really is the Stone von Neumann theorem, that says if we have a self-adjoint operator with a spectrum bounded below, then there's no conjugate self-adjoint operator. So there's no self-adjoint operator which satisfies the canonical commutation relation. So that rules out, for example, time observables conjugate to a Hamiltonian if we believe that the Hamiltonian is bounded below, or typically you'd think of it as being positive. Of course, these might be unbounded operators, so one has to be a bit careful here. And there's a better way to phrase this in terms of spectral measures. So we're saying that there's no projection valued measure on the Borel sets of R which transforms covariantly under, say, time translation, if you like, generated by A. So this is a more precise way of saying Pauli's theorem, and really it's the Stone von Neumann theorem, because we know that the representations of the canonical commutation relation are essentially unique up to isomorphism. So two good examples of POVMs that arise in this way. You can take, say, the number operator, counting, say, the occupation number of a field or a harmonic oscillator or something. And you want to say, well, is there a phase conjugate to number? And the answer is, well, certainly not as a self-adjoint operator, but one can construct covariant POVMs that do obey a covariance requirement, so they transform covariantly under phase translations generated by the number operator. Another good example is, so we'll come back to this one. So you take a Hamiltonian, any old Hamiltonian actually, but let's just take a specific one, which is multiply by the coordinate in L2 of R plus. So we just take the position operator, if you like, on the positive half line. And you say, well, is there a self-adjoint operator conjugate to that? Certainly not, because of Pauli's theorem. But there is a time observable, i.e. a POVM, living in the correct Hilbert space, values in the correct Hilbert space, well, in the bounded operators on the correct Hilbert space that transforms covariantly under time translation. And one can construct, these are not unique, but one can always produce one. And for example, one can use techniques that are quite familiar in quantum information. For example, Naimark dilation or Steinspring dilation of completely positive maps to produce such an object. So in this setting, what you do is it's this larger Hilbert space, Church of the larger Hilbert space business, where we just embed our Hilbert space of interest in a bigger Hilbert space, construct a self-adjoint operator there that transforms covariantly, and then project back down at the end. So I'm not in favor of the Church of the larger Hilbert space philosophically, but mathematically, there's no problem. Another one, one can take position and momentum and smear them out in a particular way. So one can introduce genuine unsharpness through classical noise by just taking convolutions with some measure to build joint observables for position, for unsharp, smeared position and momentum simultaneously. So one can always do this by building what's called a covariant phase space observable. So that's GT. Here, W of Q and P are the standard Weyl operators. T is a state, and one can sort of mush it all out in this particular way to build a POVM. There's one for every T. For every state T, we get a covariant observable, and every covariant phase space observable is of this form. And what one can show is that the margins of this covariant phase space observable are exactly unsharp, smeared out versions of position and momentum as spectral measures. So you can sort of produce, if you're willing to accept a certain amount of noise, you can produce a compatible pair of position and momentum, but you have a sacrifice to make, which is that you have to introduce not just any old noise, but enough noise to satisfy what are called measurement uncertainty relations. So you get a bound that's more stringent than the standard uncertainty bound here. So I'll come back to that soon. I think I've only got two more examples, and these are relevant, I promise. A really nice example of where covariant POVMs arise is in the theory of von Neumann algebras. So I'm going to come to this in the second half of my talk. So any von Neumann algebra comes with what we call an intrinsic dynamics. So von Neumann algebras are somehow dynamical objects. And this is the so-called Tomita-Takasaki theory. So if we have a von Neumann algebra M with a faithful normal state phi, one can use the machinery of Tomita-Takasaki to generate a one-parameter family of automorphisms of your algebra. And this is a really amazing fact. So there's this thing called the modular operator, which is a positive self-adjoint operator. And one can use spectral theory to write down one-parameter unitary groups. And the amazing fact about Tomita-Takasaki theory is that for any A in the algebra, this resulting object still lives in the algebra for all time. There are various generalizations, and there's a very deep connection to quantum statistical mechanics, which is if you forget about how we arrived at this modular automorphism group and just said, okay, we have a group of modular automorphisms of our von Neumann algebra, well, there's exactly one, essentially, up to isomorphism that satisfies these conditions. And this is saying that the state, the faithful normal state, has to satisfy the KMS condition. So for people from a more quantum information background, this is essentially saying it's a Gibbs state. So it's a thermal state in this theory. There's some very interesting recent work on when the time observables generated by modular automorphisms are not self-adjoint, but projection value, positive operator valued, so unsharp observables. And it seems to be true for at least, say, the harmonic oscillator Hamiltonian. And that's some work here. I've got some references at the end. which I'll refer to. So there's another example of a time observable, which is a POVM. Never-ending POVMs. This one is not so crucial for this talk, but they also arise naturally in measurement. So I'm actually not going to go through this slide. The only point here is that quantum theory of measurement leads naturally to POVMs being the genuinely measured observable in measurement schemes. And I mention it because this has been generalized fairly recently by Chris Fuster and Ryan Vesh to quantum field theory, algebraic quantum field theory. Okay, so back to quantum reference frames. Now I've motivated why I believe, hopefully convincingly, that POVMs are the right way to think about quantum mechanics. We can then start thinking about, well, is that everything, or do we need a little bit more to understand what quantum theory is really telling us? So my point of view, my starting point for quantum reference frames, as I said, is that what's truly observable in the world is invariant under whatever fundamental or perhaps even practical symmetry group you might be subject to. So in classical Newtonian physics, we believe there's a symmetry principle related to, say, Galilean invariance. So we believe that the universe doesn't fundamentally distinguish between points or locations in space or time. So I would say here that the truly observable quantities should be, for example, translation or rotation invariant. So I would say that the position of an object classically is not observable. It's not a meaningful object, but the relative position is meaningful. So the position of, Galileo's ship relative to the seashore is a genuinely observable quantity, but the position of the ship without any further qualification is not. So that's the motivation. Now, of course, one has to take a leap to say, well, what's true in classical Newtonian physics should somehow also be true in very complicated quantum theories, but one has to start somewhere, and this is where I start. So this is a different point of view than the starting point for all other contemporary approaches to quantum reference frames. So there's another approach called the perspective neutral approach, and that is somehow more constrained. So that's based on Dirac quantization of constrained systems, and it's an imposition on the space of allowable states, if you like. So it focuses in further on the observable structure somehow. So what we're going to have is a group, which is our symmetry group, or it might be a gauge group. I'm not really sure that it matters, but that's something I need to think about more. And we have some, say, unitary or maybe projective unitary representation of our group in the Hilbert space of our physical theory. So as I said earlier, if U is irreducible, then there's nothing left, right? So that's just a Schur type argument. So that's sort of a problematic situation. We can't observe single particles, even in principle. There are no observables. So this sort of hints that, well, what we're really observing is not single particles, but it's the relationship of a single particle to something else. So again, just sort of, I don't think one can prove that one should think about quantum reference frames. One can just try to motivate them in as many ways as one can until somebody believes you. So we know that invariance and relativity, if you like, or relationality are connected somehow deeply. So as I said, relative position, relative angle for rotation, and so on. And relative angles are rotation invariant, relative positions are shift invariant, relative time is time translation invariant, and so on. So somehow the invariance principle seems to push us to think about relationality in some way. So the point of view here is that, okay, we're going to introduce, of course, other systems, both to implement the invariance principle and then to say, well, these other systems are going to function as reference frames in some sense. So I'll write B of H superscript G as the space of all invariants. That's just standard notation. Inside here, there are some special ones, and I'm going to get at those next. Just a quick caveat, pretty much all of the other approaches to quantum reference frames talk about invariant states. This is just mathematically, if not suspect, impossible. So there are typically no invariant states. And I think the better way to deal with this issue is not to try to stipulate invariance directly on the level of states, but to just identify states that can't be distinguished by invariant observables. And then actually one gets quite a nice structure on the state space. Okay, so I'm going to define a quantum reference frame, which probably comes out of nowhere, but then I'm going to explain why I think it's a good definition. So I'm going to call a quantum reference frame a system of covariance. So what that actually is a Hilbert space. So, well, the starting point is a unitary representation of our symmetry group. And then we'll say, right, quotient the group by any given subgroup, isotropy subgroup, if you like, to get a homogeneous space. And then the quantum reference frame on the homogeneous space is going to be a Hilbert space and a covariant POVM on the Hilbert space. So that's one that transforms exactly in the way that we've seen in examples so far. And then once one makes this definition, one can say, well, there's a whole lot of things that stand out that one could define special cases. So we could call it sharp if the POVM is actually projection value, so there should be a subscript R here. Principal, if this is a principal homogeneous space, i.e. H is trivial. Ideal, sharp and principal. Compactly stabilized, so if we think about the stabilizer subgroup of the action of G on sigma here, it might just turn out that this stabilizer subgroup is compact. And if that's true, we end up with a much more tractable theory, so that's why we make this definition. Another key definition is localizability. So this is the E, again, should be ER, satisfies the so-called norm one property. I'm not going to say exactly what that is, but what it means is that we can localize sequences of states arbitrarily tightly in any interval. This is a property that's satisfied by all projection valued measures. I don't need to say too much about the other definitions, so I think I'll just move on. The key point for us is that all quantum reference frames can be related to a sort of standard quantum reference frame through this dilation theory. So that's going to be important soon. So let me just have a quick drink. If there are any questions, now might be a good time while I'm guzzling some water. Nothing. Good. Okay. So now we're sort of doing quantum reference frames proper. Just check the time. Okay, 20 minutes. So given a self-adjoint operator or even a POVM, but let's keep it simple, A, we can relativize by introducing a quantum reference frame. So we take our system, we introduce a frame, we sort of couple them together, and we sort of mush them together with our representation, U here. And this spits out an invariant quantity. So this yen map enjoys some very nice mathematical properties for people who are interested in that sort of thing. As a map on von Neumann algebras, it's normal, it's completely positive, so that's good for sort of quantum information reasons, preserves the involution and so on. The image is a strict subset of the invariants. So it doesn't give us all the invariants, it just gives us some of them. So we want to say, well, these are relative observables. So for example, if we take our symmetry group as just spatial translation with a representation in the Hilbert space, and we throw in the position operator here, it spits out the relative position. We can do the same thing for time or for angle and so on. So it's not just saying it gives us any old invariant, it's saying it really gives us, in those examples, something like a difference operator. So it allows us to separate system and frame in some meaningful way. Turns out, unfortunately, that in general the image is not ultra weakly closed, so we have to close it. But otherwise it functions pretty well. And from here, so we can have the relative observables. It turns out there are some nice results here about the sort of the statistical duality between the bounded operators and the trace class operators, or just the duality, reappears at the relative level. So we can quotient we can identify states on the image of this relativization map, or identify trace class operators by just saying they cannot be distinguished on the image. And it turns out that that is exactly the pre-dual of the space of bounded operators. So it's somehow saying, for me, this is compelling. It's saying that you can build a relational theory, and it's structurally it's somehow the same as the classic theory, the standard theory. And it turns out that you can this is actually related to the pre-dual of the relativization map, which is even better. So this allows us to build things called relative states. So for people who've maybe studied quantum reference frames from a different point of view, for example, Flaminia and Chaslav's work and Tom Galli and Catherine de la Hamet, for them it's a definition that all states are relative states, if you like. So you can always write down a quantum state relative to a quantum reference frame. For us, it's really a theorem that I'll explain in a minute, that you can recover relative states in a particular way. So we can fix the frame state omega, and we can define a map that sort of forgets the frame. So if we've used yen to introduce the frame, we can then restrict by forgetting the frame, it's called a conditional expectation. We just fix a state, and then it's essentially a partial trace, but it depends on the choice of state of the frame. So we can relativize and restrict. And then we get some nice things that one would expect if one forgets about the technical details and just asks some bigger picture questions. For example, if the original observable was already invariant, so the thing that we wanted to relativize was already invariant under our representation of G, what happens if we relativize and restrict again? And the answer is, well, we just get A back exactly for all states of the frame. So this is really a theorem that's saying that it makes sense to think of the invariants as the frame-independent objects in the theory, which is what one would expect, I think. The invariant quantities are exactly the ones that can be defined independently of any reference frame, in particular any quantum reference frame. I'll jump ahead a little bit. One can look for relative states of a particular form. So here we're thinking about the state rho relative to the state omega. So rho is a system state, omega is a frame state. And we get some sort of active-passive equivalence, if you like. So the state relative to omega moved a bit by G is the same as moving omega by G inverse relative to the original omega. So there's somehow a consistency between active and passive transformations. Of course, in a certain sense here, everything is active. It's just whether we're actively moving the system or actively moving the frame. I'm going to move on to localizability. So I've never called this before. I'm going to call it now the fundamental theorem of operational quantum reference frames, somewhat grandiloquently. But if we have a quantum reference frame that's localizable and principal, so that means that the homogeneous space, the space on which our symmetry acts is a homogeneous space, and the POVM allows sequences of states to be arbitrarily probabilistically well localized, so almost like delta-like. We can localize sequences of states near the origin of G, and the fundamental theorem says that any AS, any system observable that we throw into the relativization map can then be extracted again from restriction almost exactly. So up to weak. Yeah. In the weak topology, we can get as close as we like. So this is saying, I think, something profound. It's saying that the quantum theory, as we've been using it, exactly does describe quantum theory plus a quantum reference frame, exactly when the quantum reference frame admits highly localized states. Now, to have such sequences, we need a high dimension, typically, so a large frame. So this is sort of saying that the quantum reference frame has to be a little bit classical, which I think is interesting and I think is fundamental. And there's a converse which says that if we have a bad frame, there's a lower bound on the difference between these two quantities here. So it's saying that my take home is that somehow quantum mechanics was discovered exactly because we have pretty good quantum reference frames. So an application of this is a recent paper about phase space quantum reference frames. So if we go back, if you remember, I introduced a phase space translation covariant POVM. So one can actually use that to build a quantum reference frame. And then one gets something quite interesting. So I'm not going to spend too long on this, but one gets a new uncertainty relation. So we have the measurement uncertainty relation and the standard preparation uncertainty relation, but we get something as neither of these things. So if we relativize and restrict the self-adjoint position, relativize and restrict the self-adjoint momentum relative to the same quantum reference frame, the same covariant phase space observable, we get a larger lower bound on the uncertainty product, which I think is quite fascinating. I'm not sure exactly, well, it's an interesting question. So if one goes to equation 14 down here, and one takes the classical limit of the quantum reference frame. So the point here is that a covariant phase space observable is a quantum reference frame. You cannot arbitrarily well localize states with respect to both Q and P simultaneously, because we're in a phase space setting where the uncertainty relation forces us to make trade-offs. So if we're well localized with respect to Q, we're very delocalized with respect to P. So this is the first time that this has been shown to do something odd as a quantum reference frame. And we get a larger bound. So if we take the classical limit, which is completely not legal, right? So we know that quantum states obey the uncertainty relation, but we can just by fiat say, okay, our frame is a point in phase space, our frame state. So a classical state, perfectly well localized at the origin of phase space. Then one can show that one gets the classic uncertainty relation back again, the standard one. And I think one can make this rigorous using the framework of continuous bundles of C-star algebras and so on that's been developed by Klaas Landsman to make the classical limit precise, which would be a nice project. But the question is, which one's right? So is it 13 or is it 14? And I think that would allow us to say something fundamental about whether the world is actually quantum or not. Because if it's 14, then it says, well, we really have classical reference frames. So that's some recent work. Now for the next part, I realize that I've once again gone slightly too slowly. You might be surprised to hear. But I think there's a little bit of buffer time, isn't there? Maybe. Anyway, I'll just keep going. So what about quantum field theory? So local algebras of quantum field theory are typically what we call type 3 von Neumann algebras. These are pretty wild objects. In particular, there's no finite trace. So I'm going to say what I'm going to say, and then I'm going to explain how quantum reference frames might allow us to understand more about algebraic quantum field theories, or just quantum field theories, and how we might be able to compute things that we didn't think we were able to compute. So operator algebras play a massive role in the mathematical description of quantum systems. And the choice of algebra depends on the kinds of system we want to describe. So a type 1 n von Neumann algebra, when n is finite, is going to be a qubit or a bunch of qubits. So a von Neumann algebra is just matrix algebra. Things might be a little bit more complicated. We might have a particle on a line, for example. The Hilbert space is B of L2 is L2 of R. Bounded operators, that's a von Neumann algebra, what's called type 1 infinity. These get increasingly complicated. So there's something called a 2-1. Mathematically, these can be constructed as the group von Neumann algebra of some special groups with the so-called infinite conjugacy class property. They also apparently appear in the physics of infinite spin chains, in ways that I don't completely understand. Two infinities also occur, apparently, gather in statistical mechanical systems. Mathematically, if you just take the tensor product of a 2-1 and a 1 infinity, one gets a 2 infinity, and so on. And then there's a 3. So this is quantum field theory. So going back to the history of von Neumann algebras, these can be characterized fully in terms of the structure of the projections, but you can also characterize them in terms of the availability of maps called traces. So one can try to construct a map on the positive bit of the von Neumann algebra with this unitary equivalence property. We can call this a trace. We want it to be homogeneous and linear or additive on the cone. Amazing definition. We'll call it finite if it's never infinite, and semi-finite if the finite trace elements are dense. So if the trace is finite, you can extend it to the whole algebra, and it satisfies this standard trace property of being able to cycle. But it turns out that von Neumann algebras can be basically classified in terms of the traces. So type 1s are either finite or semi-finite. Type 2s are either finite or semi-finite, and type 3s are very much not finite. So if you think about, well, we might want to compute a von Neumann entropy. How are we going to do that? We're going to take the trace of rho log rho. Well, that's not very good if we don't have a trace. So this is an issue, right? So there are these famous results going back to Hawking and Bekenstein and Gibbons and so on, that propose that the areas of a horizon of a black hole, or say a cosmological space-time, should be understood as entropies, or at least related to the entropy. Well, how are we going to make that rigorous in quantum field theory properly if we know that the quantum field theories are type 3 von Neumann algebras and there's no trace, hence there's no entropy? So there was a recent piece of work on this, CLPW, where they say, okay, let's look at a particular model. Let's take a space-time which is a portion of de Sitter, the so-called static patch. So that's the bit of de Sitter that's accessible to causally accessible to an observer. So the bit that you can get to with light rays and so on for any observable in de Sitter. So you pick an observer and you sort of causally complete it. So what they found was if you introduce an observer traveling along a world line in this static patch, you can, via some magic, move from a type 3 von Neumann algebra, which is the quantum field theory, to a type 2-1. This has been called type reduction, I think accidentally. I don't think anybody knows quite where this came from. So there was some recent work that I'm going to talk about by Chris Fuster, Kasia, myself, James Waldron, and Dan Jansen, also in York, where we say, well, the quantum reference frame, or the observer of CLPW, Chandrasekharan, Longo, Pennington, Witten, is nothing but a quantum reference frame. So somehow there was a theory ready and waiting for understanding their result and for generalizing it fairly significantly, I think. So what's the big picture? I should say, by the way, I'm not an expert in quantum gravity. There is some other work on this that's by Philip Hearn and collaborators that's somehow a more quantum gravity setup, again using constraints. So if you have any very difficult questions on quantum gravity, I will happily defer you to the co-leader of the working group, Kasia, who will be absolutely delighted to answer the difficult questions. Hope that's fine, Kasia. It's only
Always.
you two. Okay, so the big picture is that so we might have a space-time with symmetry, or it might be even more. We might want to consider diffeomorphisms, but either way, a theory based of local measurements based on a space-time that might have symmetries seems to break symmetry invariance. We say our measurement happens here and not here. That has some tension with what we were saying earlier about the role of symmetries in quantum measurement or quantum field theory. So we're going to say, right, we work in the framework of algebraic quantum field theory, which has its own set of assumptions and so on. So this is not quantum gravity. And we're going to work on a background that has symmetry, genuine symmetry, so isometries of the manifold, not diffeomorphisms in general. So again, in the spirit of what we've been saying, the true observables are going to be the isometry invariant quantities. So we're going to introduce a quantum reference frame just as before. And what we're going to do is analyze the type of a quantum field theory on a background with a particular isometry group, which is R, which is basically going to be time translation times some compact group. And we're going to introduce a quantum reference frame, which is compactly stabilized. Why we make these definitions is because that's the place that we're able to prove some nice theorems. One should also go beyond this and generalize it. And this talk is called an invitation to quantum reference frames because we need manpower or person power to continue this work. It's a lot of stuff to do. So as I mentioned, there's other ways to do it. This is just our particular way to do it. And we're going to use some of the machinery of von Neumann algebras and so on. So I realize that I'm very low on time, but I probably need another 10 minutes. Is that acceptable? Or should I try to do it in 5? You can just put a thumbs up, thumbs down.
You can go ahead for a bit longer.
Okay, good. Okay, so I will skim actually the details and maybe not the main points. So I just want to show everybody how utterly clever we are by writing down all the details. That's not true. So what we're trying to do here is say, take a quantum reference frame, relate it to a standard quantum reference frame via what we call a covariant Naimark dilation. So that's always possible. Goes back to, well, Mackie, very old, and Cataneo, less old. So we take our quantum reference frame and we just embed it in some bigger Hilbert space where we have the left regular representation of our group, lambda acting in L2 of G. And then our frame observable E is related to the projection via this isometry that appears in the Naimark dilation. One can sandwich these two things together. If you have an isometry, that always gives rise to a projection in the following way, called the Naimark projection. And then we just show that there's always a way to write our QRF as the, what you call it, projection or compression of this standard quantum reference frame. So that's machinery. Take our QRF, make it bigger, do some nice things using representation theory. So Mackie and Cataneo together showed that all of these things are sub-representations of induced representations, and then you can just project back down again. So we have a standard quantum reference frame. We have a quantum field theory, MS, that's a von Neumann algebra. We'll think of it as acting in some Hilbert space via some continuous action. We have our quantum reference frame, and we want to analyze the structure of the invariant algebra. Right, that's what we need to know. So we don't know how to do that in general. That's a difficult thing to do, but we do know how to do an easier one, which is this should be an MS, M tensor B of L2 of G, right? So that's our regular representation. And the invariant algebra is completely characterized in terms of the cross product by this action. So a cross product is a sort of clever gadget. So it says if we have a group acting on a von Neumann algebra, is there a von Neumann algebra that somehow encodes that group action? And the answer is yes, it's called the cross product. It's basically exactly the same, or exactly analogous to when you have a semi-direct product of a group with a subgroup. So you say you have an action of a group on another group. Is there a group that somehow knows what that other group is doing to the group? And the answer is yes, it's the semi-direct product. So there's a way of building the group action into the algebra to produce a larger algebra. So what we do is embed our setup in the cross product setup and then project back down again. And then say, well, what do we get? So this is reported in a long paper. There are many technical details, and there are many simplifications one can make. For example, if the action of a known algebra is implemented via some unitary, everything is a little bit easier. But in the setting that things are simple, one can actually do quite a lot to say what the structure of this new algebra is. So if we assume that our von Neumann algebra has a KMS state and the modular action, so we have a modular action on our von Neumann algebra, we embed it, etc., etc., etc. What we see is that the actual algebra of invariance here, where now we're just looking at the action of R, can be related to the cross product with some other gumph and then projected back down again. So what we want to say is, what is the structure of this algebra? So there are many known results about cross products and the type of cross products of von Neumann algebras. So what we find is that we can use all of these results that have been known for some time and the covariant dilation theory to show what is the structure of the resulting invariant algebra of our quantum field theory plus our quantum reference frame. So we can show that we can construct a semi-finite trace on the algebra, and that's finite exactly when this projection, this Naimark projection, has a finite trace. Now we can show that happens exactly when the frame admits basically a KMS state, slightly more general, has to be a weight at the same inverse temperature as our quantum field theory. So that is something that's perhaps slightly mysterious. It's a sort of thermal equilibrium property. And we can show that if the subgroup H is trivial and our quantum field theory is a 3-1 factor, which they're typically assumed to be, then we get a 2-1 factor out again. So I'm going to state this as a theorem, and then I'm going to explain exactly how it works in the CLPW model, which is slightly less, my mouse is being, which is slightly more obvious. So the statement of the theorem is, if we have a quantum field theory, MS, with a KMS state acted on by G, which is just R across a compact group, and we couple it to a compactly stabilized quantum reference frame, then the algebra, the invariant algebra of system plus reference frame, don't know why it's doing that, is semi-finite, i.e. admits a semi-finite trace. Then if the frame admits a particular KMS weight, so that's a little bit more special, at the same temperature as the quantum field theory, then we get a 2-1 algebra. This algebra is finite. So we've gone from a 3 to a 2, in particular a 2-1. So take home is that you can start off with a very wild von Neumann algebra, type 3 von Neumann algebra, introduce a quantum reference frame, analyze the structure of the invariants, make some assumptions about the frame that are not that outrageous or that particular, and one gets a 2-1 back again. So this happens in stages. So we take the cross product with a particular action of the real numbers, the modular cross product. The modular cross product takes us from a 3 to a 2 infinity, and then this 9-mark projection takes us from a 2 infinity to a 2-1. So this is a two-legged beast. Interestingly, the non-triviality of this 9-mark projection means that the quantum reference frame is an unsharp time observable. So that's a sort of Pauli theorem for type reduction in a certain sense. It's not known exactly which unsharp time observables do it. So we have some sufficient conditions. We don't have any necessary conditions. The interpretation is not super clear. The new theory is a 2-1 is somehow, well, isomorphic to a spin chain, an infinite spin chain, just as an algebraic object. We're not saying that what comes out is a quantum statistical mechanical system, but it's a different kind of beast than the quantum field theory that we started with. And the final comment really is that we haven't said anything about gravity at any point. So we do have a curved space-time with a particular isometry group, but we're not saying that this is sourced by a mass or anything like this. There's no quantum gravity here. There's just a curvature. So there's a lot of talk about saying that gravity regularizes quantum field theory, but it's not clear in this framework that that's what's happening. So I just have one more slide where you can see the CLPW Hamiltonian, so I introduced this one earlier. If one just looks for the time translations, everything's much easier. So what we see in equation 20, just to say it very clearly, we have our quantum field theory, which is type 3. We take the cross product of the modular action of the real numbers. That's just time translation. This thing is a 2 infinity, and then this P plus that takes us from L2 of R plus to L2 of R back down to L2 of R plus is a projection that takes us from a 2 infinity to a 2-1. So there's sort of two stages, and it's that final stage that turns the sharp time into an unsharp one. And for me, that's a really fascinating piece of the puzzle that's not been analyzed yet. So what's the summing up? So quantum reference frames are indispensable for describing quantum mechanics and quantum field theories under symmetries. I have a personal belief that actually these will also be crucial for understanding quantum measurements in general and the kind of world that's described by quantum mechanics. So people who have a philosophical background or interest, we could discuss that. QRFs are sort of springing up in many other areas, quantum thermodynamics, stuff like that. And there's a ton to do. So, this is a cost action working group on relativistic quantum information and quantum field theory. We do not have a fully quantum field theoretic quantum reference frame in this setting. This is a quantum mechanical quantum reference frame. So there's also work to do in that direction. So with that, I will rudely finish 10 minutes late and just put some extra references that I didn't reference as I went, but otherwise, for anybody who's still alive, that's it.
Thank you very much for very nice talk, Leon. Are there any questions, comments? Yes.
Go ahead. If there are no other questions, I will exploit my role as the organizer of the conference to ask some, of the seminar to ask some questions. So thanks a lot for the interesting talk, Leon. So I had a few different questions. Maybe one would be when you were presenting the frame relative uncertainty relations.
Mm-hmm.
Just I would like to understand them a bit better. What that would sort of operationally mean to have sort of uncertainty relations that are really dependent on your frame, because the way I would think of uncertainty relations is really because they have some operational meaning in terms of what one can measure. And this would be, for instance, directly related to like security of a cryptographic protocol if one thinks more in this operational sense. So in this context, if you were to imagine that these can become frame dependent, is it more that somehow the observable for which you're speaking about the uncertainty relation, or the system for which you're talking about, changes? Or is it really, in some sense, the uncertainty in the same observable that changes? Yeah, it would.
Yeah, no, it's a good question. Like, it's not completely clear, and I think it depends a little bit on what you believe quantum reference frames are actually really doing. So my point of view is that quantum mechanics is not describing what we think it's describing. So it's really describing the relationship between a system and a frame. It just so happens that usually we can forget that there's a frame. So, and we can do that because of this this fundamental theorem of QRFs, if you like, that you can always build a frame that localizes arbitrarily well. So you can forget about it. So that's sort of what a good frame does. It's something you can forget about. So in the setting of uncertainty relations, it's a little bit confusing because I don't know exactly what to think about it, because the point is that you can't have an arbitrarily good frame for Q and P simultaneously. So if you just live in Q world, you can localize as well as you like with respect to Q, and then you can forget the frame. So there's no issue. But of course, what you're forgetting is that, well, that's going to completely mess up P. So I'm not sure if that's really answering your question, but I think what I think about quantum reference frames in this language is that the standard textbook framework based on a Hilbert space, bounded operators, and probability distributions, we're not actually describing quantum systems as they are, but quantum systems relative to a fairly classical, or maybe completely classical reference frame. So in a sense, it's not that the uncertainty relation here is sort of frame dependent in the sense that we could find a frame where we remove the uncertainty relation or something. It's saying that the actual uncertainty relation as we know it is wrong if we believe that they should be understood relative to a quantum reference frame for Q and P simultaneously. So if that is the case, what we're saying is that there's a Galilei symmetry. So I didn't really say it, but here we're really assuming equal mass. So we're assuming that velocity translation symmetry is the same as momentum translation symmetry. So it could be that large mass of the frame actually just messes this up. It's really difficult to do this. The relationship between velocity and momentum in quantum mechanics is really confusing and difficult to deal with somehow. So I think this is to be just determined by experiment. I'm admitting my ignorance here, but I don't actually know to what extent the uncertainty relation has been verified experimentally, particularly the measurement uncertainty relation. So the one that's sort of a little bit bigger. So this one. So it could just be that actually this is the right bound, 3/2, not 1/2, and that's so far within the realms of experimental error so far that nobody's noticed it. Or it could be that there are actually in the world fundamentally classical systems, or systems that can be, at least in this setting, treated as being perfectly localized in phase space, in which case then maybe this is the right bound. So I think that's something I need to understand better. But in terms of, I mean, I've been doing this for so long that I now really believe that that we have to go back to everything, like Bell's theorem, Cauchy-Specker theorem, quantum computing. Somehow it's difficult to unsee it once you've looked at it for too long and think that everything is actually relative to a frame. Somehow I think we have to reconsider quantum mechanics completely from the beginning. So of course, then we'd also have to look at the sorts of things that you're talking about.
Thanks. Thank you. That's very interesting. Any other questions?
I don't see any. So yeah, maybe let's close it here, and thanks, Leon, again for nice talk and the discussion. Thank you.
Very welcome. Thank you very much for the invitation.
Thanks very much, Neil. Yeah.